Hello and welcome to a continuation of a previous episode of How to Understand X, that being limits. I think this video is going to be probably not too long. I mean, I don't have a good track record of sticking to that assumption, but I'm not going to talk about anything other than continuity and indeterminate forms, I think. If something comes up, then I'll probably talk about it, but for right now, let's talk about the most important thing. Something that I didn't even mention. Well, I mentioned because I realized how dumb that I didn't say it, but yeah, no, continuity is really important for figuring out when a limit even exists. So making a limit video without addressing when a limit exists is just incredibly stupid. But yeah, let's talk about when a limit exists. And before we talk about when a limit exists, we need to talk about what continuity is. It's almost exactly what it sounds like. Continuity is, so the formal definition of continuity is if you are given a function f of x, f of x is continuous at x equals, let's say c, because we worked with c on that derivative video, at x equals c if, let me write that down. This is gonna seem counterintuitive, having to define limits by defining continuity, which uses a definition of limit, but I think it's pretty intuitive. If the limit as x approaches c of f of x is equal to f of c. In other words, f of x is continuous I'll just abbreviate that, on the closed interval a to b if it is continuous at every single point. And what does that mean? Well, since we know what a limit is, and we have to use what continuity is to define a limit in the first place, or where a limit exists, it almost seems like circular reasoning to try and define continuity using limits, but it's not too hard once you at least understand it, if it is continuous at each point on the interval. So, what does that mean? Well, let's think about it. If x is equal to c, and the limit f of x is equal to f of c exists, that means that at the value x equals c, from both sides of the equation, if we think about how we define limits, from both sides of the equation, let me draw some random function like that, and let's say that that point is c. If we're saying that a limit exists at x equals c, we're saying that, I'll bring up our formal definition that we talked about, but right now I think you at least know what a limit is pretty well, and we have to say that from both sides, c, or f of x, approaches a y value for the x value c. And that's enough, almost. But you forget that the limit as x approaches c of f of x has to equal a real value, f of c. And let's think about what we have drawn and kind of assumed from here. If the limit of f of x as x approaches c exists, that means that from both sides f of x has to approach a value in which the x value is equal to c, and then the y value is real and exists. So for C, I know I'm using a bunch of arrows, but still. So the pieces of information that we've gathered so far, f of x has to approach a y value for an x value c, and it has to approach this x value c from both sides. And this y value needs to exist for the function to be continuous at x equals c. And that was kind of a word salad, but it just means that if there is a point x equals c, there needs to be a point f of c. And that point needs to be approached from both sides. Just remember, both sides is a really important thing for limits and continuity. It needs to approach from both the left and the right, or in more like mathematical terms, I guess, it has to be able to approach from positive infinity and negative infinity. As the x values tend from negative infinity, which is again not a value that's like possible to express as a number, so we use a parentheses, and it approaches c. That's what this notation means. There's the open interval negative infinity to c, and c to infinity. F of c must exist. So you might even actually write this as, instead of parentheses, you can use brackets to show that c is a value that is being approached from both sides. And now, I know that this c is double written, but from here, let's think about this. So we have a closed bracket c on both sides, and we have negative infinity to infinity. So you might even write this as a negative infinity to infinity. And that's true. You're saying that if c is a value that is approached from both sides, and negative infinity is from the left side and positive infinity is from the right side, there is an interval negative infinity to infinity. But in order to see whether f of x is continuous on negative infinity to infinity, we might have to look at our second little sentence here, and that's the one that I've been trying not to erase. And that is, f of x is continuous on the closed interval a to b if it is continuous at each point of a to b. And the reason why we can't use the open interval negative infinity to infinity is part of the second sentence, if it is continuous at each point of a to b. If it was continuous at each point of a to b, if we remember our first part, the limit as x approaches f of x, the limit of f of x as x approaches a has to equal f of a. I'm just substituting c for a in this. And if that's true, that means that there is a limit at the end. Or, well, I don't want to catch myself in a hole, but, there has to be a value where the limit as x approaches a of f of x is equal to f of a. And that doesn't seem too bad, because if we were to try and use the open interval negative infinity to infinity, if we had, let me write that, x approaches infinity, we should theoretically be able to substitute infinity into x and get a value. But that's not really how it works. Sure, you can substitute infinity, and you might even get a finite value if you try and do a limit. we talked about this in the previous video, but the limit as x approaches infinity of f of x is if f of x equals 1 over x is 0, because, as this x grows larger and larger and the 1 stays constant, eventually you will be trending towards 0. But I tried to hammer it home that 1 over infinity is not equal to 0. It trends towards 0. Because, again, infinity is not a number. It is an idea, a concept. So you can't substitute infinity for anything. If you had f of x equals x squared, infinity squared, maybe it might work with math. You can say, oh, infinity squared is infinity. So infinity is a number, but that's not how it works. Infinity is still a concept. So regardless of whether the limit is a finite value, this number, if you were to just ignore the number, if f of x equals f of infinity, that's not possible, because 1 over infinity or infinity squared or any operation that involves infinity is not a number. It just trends towards some number or some really large or really small number. So this second part of our definition of continuity doesn't really fit with our idea of open and closed intervals. And that's okay. We can't. The reason that we're trying to constrict ourselves to closed interval is because I don't want to get into axioms or anything weird, but if we were to try and say that f of x is continuous on the open interval negative infinity to infinity if it is continuous at each point of negative infinity to infinity, it would not take a finite amount of time to prove that. So we must assume that this f of x is continuous on negative infinity. This is an assumption, so we can't immediately say it. Since a to b is closed, then we might be able to prove that f of x is continuous on that closed interval. But with the idea that we are using the interval negative infinity to infinity, we have to use an assumption that f of x is continuous on the closed interval, open interval, negative infinity to infinity, if it is continuous for most values of negative infinity to infinity. Because we'll never be able to plug in every value of negative infinity to infinity. So, yeah, I said infinity a bunch there, but essentially the reason why we're using a closed interval is because the open interval, negative infinity to infinity, is not something that we can try and find continuity of in our lifetime. So with the second part of our definition of continuity, f of x is continuous on the closed interval a to b if it is continuous at each point of f of a to b. That means that for every value in in a to b, there has to be a limit as x approaches that value, and the value must exist. So f of c must equal the limit as x approaches c of f of x for every c in a to b. I know that's a bunch, and I'm not trying to make it abstract, but I know how it comes across. Just every value within this interval, every real value. Okay, I don't want to get into how infinite real values are. Okay. I don't want to get too bogged down by the details, but I always thought this was pretty cool. I don't like infinity, and I will die on that hill, but I thought that this was always an interesting idea. I'm going to leave this sentence here so I can at least remind myself if I'm getting too off topic that I'm trying to talk about continuity. But a to b is filled with an infinite number of real values. And that might sound crazy. there are an infinite number of, if we use our C's, there's a C1, a C2, a C3, and on and on. And you might think, well, we'd be able to catch all of that, right? And that's not true. If you'd like to see the proof for why the number of real numbers between any two numbers is uncountably infinite, you can comment down below. But essentially, let's talk about the. I'm getting far too off topic, and I'm conscious of that, but I just thought this is interesting. So, the set of natural numbers, which is 1, 2, 3, 4, 5, and on and on and on, that is countably infinite. I have no idea how to show Aleph null. It's like a. I'm not even going to try and draw it. But this is countable. That's because if we assume that there is a first element, and that first element is at 1, and if we assume that any addition of natural numbers is a natural number, like 1 plus 1 is 2, which is a natural number, and 2 plus 5 is 7, which is also a natural number, we can say that for every natural number that already exists, you can add 1. Like if you do 1 plus 1, you get 2, and 2 plus 1 equals 3. And then 3 plus 1 equals 4. And while that would obviously take forever, it's technically possible to count every element in, well, it's not possible, like by a human or like a computer that lasts for 3 trillion years, because there's always another way that you can add the element that you're on, and you can add another one. But this is what we'd call countable infinity. There are operations that we can do to show that it is countable. And as for z, which is, you know, it starts really, really small. I'm not going to put negative infinity because I feel like I'd be confusing even more people than I already am. But let's say that eventually you'd get to negative 5, negative 4, negative 3, negative 2, negative 1, and then 0, and then 1, 2, 3, 4, 5. And this is also countable. Even though we're starting at a value that doesn't exist, we could split this into two sets, union 0. I don't want to talk about union right now, but we can say that from, a really small value to negative 4 to negative 3 to negative 2, negative 1. I'm not going to do a formal proof of this because that would take too much time. And then, okay, this is getting too cluttered, but let me write that slightly better. So z, which is the set of integers, if you go from a really small value to negative 5, to negative 4, to negative 3, to negative 2, to negative 1, and you let that be a set. A set is just an assembly of a bunch of elements. And then you union that, or add that to another set, which just includes the element 0. And then you union that to another set, which is 1 to 2 to 3 to 4 to 5, and on and on. This is also countably infinite. I'm not going to show you why this part is countably infinite. We know that this is countably infinite because of the n plus 1 thing. And we know that it's just one element. We can count 0. But this is kind of like the inverse of that set. For a negative 1, there is a 1. For a negative 2, there's a 2. For a negative 3, there's a 3. For a negative 4, there's a 4. And for a negative 5, there's a 5. And on and on. So we could count that. And now we can get even crazier. And I can't even write the rational numbers, but Q, what an awful Q. I'm trying to do like that thing where you draw a circle on the inside and then that, like that. That's the fancy Q that you use for this stuff. But I can do that. Let me try. Sure. That is the rational numbers. Like every possible expression of 1 over 1, 1 over 2, 1 over 3, and then you eventually get to 2 over 1, 2 over 2, 2 over 3. Just every expression of a ratio, that is possible. That is also countable, because for every ratio, you are using two numbers that exist that are countable, and for every assembly of a ratio, a over b, there will be an a and a b that you can express, and an a over b that you can also express. So while these are, obviously different sets, the cardinality. Oh my god, what am I doing? I'm trying to talk about continuity, and now I'm on a completely different topic. But this is interesting, in my opinion. So, the cardinality, or the number of elements, um, is weirdly equal for the. I really hope that Q is rational numbers. I'm pretty sure, because I think that R is real, which we will talk about, and I will eventually get to the point of what I'm trying to say. But since we could spend, theoretically, all the time in the world counting every natural number, every integer, and every rational number, we would say that the cardinality of all of these infinite sets, even if our brain tells us this one has less elements than this one, which has less elements than this one, their cardinality, or the number of elements, since we can't actually count all of them, is equal for all of them. But, and finally I'll get to my point, natural numbers, integers, and rational numbers, they're all countably infinite, but real numbers are not. Real numbers are not countably infinite, because let's constrict ourselves to just 0 to 1. The number of real numbers between 0 to 1 is um, is uncountably infinite. So a real number, well, you know what a natural number is. It's just one, it's every number that is positive and not 0, and that is a whole number. And then the integers is every negative whole number, 0, and every positive whole number. And then rational numbers is just every ratio of numbers. So real numbers, it's a little bit hard to explain, but you can just kind of say it as every assembly of digits that can represent some kind of distance on a number line. That's probably the best way to say it, but it's still weird. So like 0, let's actually use our 0 to 1. With a 0 to 1, you have your 0.5s and stuff, but you also might have like a 0.7963241, and on, with no digits ever repeating. And so let's talk about 0 to 1 as a closed interval in terms of n, that was wrong, n, z, and q. So if we talk about 0 to 1 in terms of n, z, and q, well, the amount of elements in n that are n 0 to 1, there's only one, and that is 1. Because if n is 1, 2, 3, and on, that doesn't include 0. So n is kind of boring. We just have 1. But for z, since the integers include 0, we'd be left with 0 and 1. And now, in q, there's a lot more elements. You'd have 1 over 2, 1 over 3, 1 over 4. And eventually you would get to 2 over 2. After a bunch of countably infinite values, you'd get to 2 over 2 and you'd stop. There is a stop eventually. But for the number of real numbers, there is no stop. If rational numbers are the expressions of a ratio of two numbers. Real numbers are just any distance possible. So again, there will be like a decimal that can go on forever with no repetition of values. Every rational number can have a repeating value after a certain amount of time. Like 1 over 2 is equal to 0.5000, and that 0 would always be repeating. Even though we don't write it, we know that in our heads. And 1 over 3 is equal to 0.3333, and that 3 is repeating. So um, maybe a way of thinking of rational numbers is as a decimal that will eventually reach an infinitely repeating value. But real numbers will never have that. There will never be any 2, 2, 2, 2, 2, because then it would become a rational number. We might be able to find some type of ratio of two existing numbers to make that. So if these digits never repeat, I'll just throw some numbers. There will also be like a 2, 3, 1, 9, 8, 5, and that never repeats, and on and on. And it's so much larger, and it's so hard to imagine, but the number of real numbers is just so large that even on the closed interval, 0 to 1, the cardinality, or the number of elements in R, just in this interval, is greater than the cardinality of N, it's greater than the cardinality of Z, it's greater than the cardinality of Q. So, eventually, I will get to my point, I promise. If just the number of real numbers within 0 to 1 is larger than any of the infinite sets that we can think of, the closed interval a to b, you might be saying, wait, if there is a value for every f of c, if c is in something, if f of z, let me write that, if f of c exists because c is in AB, you might be thinking, how could we possibly prove that A to B is continuous if we can't plug in every real value between A to B, because that's just uncountably infinite? So what do we do? Well, uh, um, I guess the mathematic way to answer that question is don't worry about it. I know that's unsatisfactory, but since we're working with limits and continuity, uh, the reason why we have to make this assumption is because we're just choosing not to worry about it. Yeah, I know after such an incredibly long and tangentially related build-up, we've gotten to such an unsatisfactory answer. I know, I'm sorry, but even though there is an uncountably infinite number of real values C inside A to B, there's no way to, well, there might be a way, but there's no way to prove that there is a value, there is always a f of C for an A to B if, well, I mean, you could prove that, but you can't say that there's always going to be a value f of C in A to B, because there's just an uncountably infinite number of C's inside A to B. But for our purposes, if we say that f of x is continuous on the closed interval A to B, we're gonna try to avoid using real numbers, because we can't calculate any operations on real numbers because they go on infinitely without any repetition. So we're going to only be working with rational numbers within a closed interval, and then, we might be able to do something with that. But if f of x is continuous on the closed interval a to b, and that means that it's continuous at each point of a to b. So every c that we can calculate has to exist within that. And I know the vast majority of what I said is it's not related. It's completely unrelated to continuity, and it might even be like just boring and useless. But I thought it's interesting, and yeah, I guess I know I don't know why I'm like talking about continuity like this. Very essentially, continuity is if you are given an interval, you must be able to calculate everything that you can calculate, every input that you can calculate. You should be able to calculate that input, and you should be able to get some type of output. That's what continuity is. For every input that is calculable within a interval that you are given, you should be able to find an output there. And so with that, let's talk about discontinuity. And that's kind of it's exactly what it sounds like. Discontinuity. If we use our STEM knowledge, we can say that dis means away, and discontinuity is when a function is not continuous. And now you might be thinking, where are functions not continuous? Off the top of my head, I can tell you that there is removable discontinuity. Let me just break it down into the three ones that you're absolutely going to see. Removable, jump, and let me check 1 second. Okay, yeah, I think it's called infinite discontinuity, but we have these three, and then the fourth, and perhaps the most interesting in my opinion, is the fixed discontinuity. Or no, it's not fixed. It's endpoint. Okay, sorry. Endpoint discontinuity. And these are all kind of what they sound like. Removable means that there is something that can be removed. And if we are saying that there is a removable discontinuity, we're saying that when we are given a graph and we are told that there is a closed interval a to b, in our heads we know that from our definition of continuity, for every input in a to b that we can calculate, there must also be an output that is calculable. So with that, let's draw a graph like that, and let's just put something in there. You might have done this before, but this open circle means that there is no value, and then this closed circle means that there is a value. I almost put closed, but there is a value. And within the context of this, if there is no value, that means that there is no output. So even if there was an input, let's say that this is some x equals c, if we were to plug in the x equals c into our f of x to get f of c, if there is no value at f of c, that means that f of c does not exist. I'll put d and e from now on. That means just does not exist. So the value f of c does not exist, which means that the function is not continuous at x equals c. And if a to b is these values, that means that a to b is not continuous, or f of x is not continuous on a to b. And that's exactly what it sounds like. If you might even think of continuity as like walking on a sidewalk. And this might be a weird sidewalk, but if you are a person, and let me try and draw it like, no. So if you were given like a racetrack that goes like that, and you are walking. I'm just trying to say, like, if this was, the y and x axis, that would be an appropriate x squared. And if you were to just keep walking, if there was a hole or a removable discontinuity at some x equals c, you wouldn't be able to walk on every step of the racetrack. You just kind of fall through. So, yeah, that's what a removable discontinuity is. It might be also called a hole, um, because there is a value that does not exist. And for every value in A to B that we can calculate, there must also be an output. For every input value, there must be an output. So, yeah, that's the removable discontinuity. Now, the jump discontinuity is also pretty interesting. I don't know why I made my arrows so grotesquely large. I'll just, that this goes on forever. But jump discontinuity is kind of interesting to me. So it's like this. If that's our function f of x, f of x can also be a composite function, and we can say that it continues from here to like that. Now, sure, let's look at that for a second. If we are given our a to b, and that point where everything weird is kind of happening, C is there, A to B. Well, this jump continuity, I think I could define something really quick. So f of x is the two functions x squared for x is less than c. Like every value to the left of c, it generally follows x squared. And now for x is greater than or equal to c, because as you can see, I used a closed circle. Well, maybe you might not see it, it was kind of a small one, but yes, that is a filled in circle. So there is a value at x equals c, so x can equal c. Let's say that this kind of looks like it's going for maybe 3. Let's say that this is 2x plus 3. Sure. So, what gives? This looks like it might fit in with our definition of continuity. Given a to b, if f of x is generally following the trend, for every c value of input, there is a c value of output. If we are given an f of c that does exist, we have a filled in hole, why exactly is this discontinuous? Well, this is going to link back to our definition of a limit. I kind of hid that, hoping that somebody might remember the first part of our definition of continuity, but it's not just f of c has to exist. We have to say that the limit as x approaches c of f of x has to exist, and it has to equal f of c. I will go back to our formal definition of like limits in just a little bit to really cement our idea of continuity, but if you remember, as x approaches c, it has to approach c from both sides. It has to be negative infinity to c and c to infinity. And f of c must exist. It must be a value. And that's not what's happening here. From this side, c is approaching c squared, because, f of x is equal to x squared for x is less than c. And then from this right side, we have x is equal to 2c, well, not x is equal, y is equal to 2c plus 3 if c, oops, I should have put an arrow instead of a equal sign, but we're saying that for the x value c, y is tending towards 2c plus 3. And in this case, just as we can see, I'm sorry, um, just as we can observe better, c squared does not equal 2c plus 3. It might equal 2c plus 3 in some other unrelated thing, but as of now, um, for our value of c, it does not equal, c squared does not equal 2c plus 3. And that means that from both sides, the limits don't exist. I mean, the limits exist from both sides, but they do not converge to one point. The limit from the left side is not equal to the limit from the right side. And that actually gives a very good idea of when something is differentiable too. But I'll talk about that in just a little bit. So yes, this is the jump discontinuity. When even though f of x does have an f of c for every value of a to b that we can calculate, f of c is not the same. Well, yeah, not f of c. The limit as x approaches c of f of x is not the same from the left and from the right. So that means that there is a jump discontinuity. And then the third of these discontinuities is the infinite discontinuity. And this is just kind of what we were talking about. You can't calculate every value within negative infinity to infinity because that's not possible within our time. And if just the number of real numbers between 0 to 1 is uncountably infinite, then the number of real numbers between negative infinity to infinity is just unimaginably large. The number of elements within that real elements is just, it's impossible to even think of. So, given this, you might think that these infinite graphs look really crazy, but I guarantee you've probably seen them before because these are asymptotes. We're saying that, let me try drawing that without having my hand shake so much. The infinite discontinuity. If we have this axes, let's say that we are going towards some really large value, and spoiler alert, it's positive infinity, and we are also going to a negative value, then this is also negative infinity and positive infinity. And let's say that this asymptote happens at x equals c. And these are our trusty a's and b's. Now, for almost every value, I know this might seem weird, but for almost every value in a to b, actually for, do I want to say for every value? I don't think I can. No, I think I can, yeah. So, for every value, every real value in a to b, there is an f of c, except, no, I'm not going to use f of c. Let me say f of x. For every real value of a to b, there's an f of x for that real value that does exist. But for f of c, there is not a real value. Not only is infinity and negative infinity both numbers, I mean, not numbers, they're both ideas, so you can't actually express it as a number, but also just using our common sense, if we say that from both sides it has to approach a real value, f of c, if the limit as x approaches c has to equal f of c itself, while this might be something, this might be infinity, f of c cannot equal infinity because infinity is not a number, it is a concept. So, yeah, this function is not continuous at x equals c, even though for every real value of a to b other than c, there is a value x equals c, it just doesn't exist. And you might try and be a little bit crafty and say that there's actually a line that goes straight through, but that doesn't work either. Since x equals c is a real point, there's no possible way of connecting like c minus some arbitrary h and c plus h if h is some really, really, really tiny value. Even if we tried to like make it so that c minus h is equal to c plus h, it's just not possible. So yeah, infinite discontinuities is just what it sounds like. Um, Let me try and erase that without erasing too much. And it's kind of I think it's the least interesting of these infinities. I mean, least interesting of these discontinuities, but I mean, it's the one that you might see the most. And now, last and certainly not least, we have endpoint discontinuity, and I think this one's the most interesting. So I'm gonna use a function that you have almost definitely seen before, and that is square root of x. F of x is equal to the square root of x. And now, I know that I kind of let it go out a little bit, but there is a value of x at 0, and that value is f of 0, or 0. So f of x does exist at x equals 0, but f of x is not continuous at x equals 0. Sure, f of c does exist. I'm just going to use c because that's what we've been talking about, but c equals 0 for this one. F of c does exist, but the limit as x approaches f of c, not f of c, as x approaches c does not exist. As x approaches c, we do not get a value. And you might be wondering, well, why? And that's because there's nothing to the left. Even if we have a to b, we can't say that f of x is continuous at that value because the limit does not exist at that value. So even if we have a to b right here and right here, they seem pretty normal. I'll even erase our c, and yeah, sure, I'll erase these and make them a's, just so that we can go back to our a to b close notation. If we have the limit as x approaches a of f of x equals f of a, sure, f of a is a value, but the limit as x approaches a of f of x is not a real value, because from the left and from the right, the function needs to approach a value for a limit to exist. I will talk about that. Actually, no, I'll talk about that right now. You might want to write that down, maybe? I don't know. But, yeah, so, if you do remember our formal definition of a limit from that previous video on limits that I did, we are saying that if f of x is defined for all x in an open interval that contains an a in some interval of, let's say, Actually, no, let's use C instead. From A to B, let L be a real number and then say that the limit as x approaches C of f of x is equal to L, and L is a real number that exists. So for every epsilon that is greater than 0, there exists, I'll just show you a little bit of math notation. That means there exists. This is there exists. This is for all. You might want to write that down. Maybe not this stuff, but you might want to put there exists if you're not used to that notation. And this means in, that's not epsilon. This is like for n in real numbers. So for a natural number n, did I say real numbers? I meant natural numbers. And, there's a bunch more symbols, but this backwards looking E means there exists a delta greater than 0, such that, and st is equal to such that. I know having to write this out kind of invalidates the point of abbreviation, but still, it's a good thing to know if you want to eventually write proofs of your own. St, such that if, maybe write this down, I kind of like gave myself way too little room. I'll actually, you know what, I'll do it again. So for every epsilon that is greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta, then f of x minus L is less than epsilon. And that's basically saying that as, or did I think I switched to C instead of A. But yeah, for every C value, there is going to be for every C value, which again is an x, since we defined C as an x value within the interval A to B. Well, it's an open interval. Since C is a x value in the open interval A to B, that means that there is a C value x, where, there's an x value C, where there's a kind of like a range, or a domain. Yeah, there's a domain of negative delta to delta that surrounds this. Since we have the absolute value right here, that means that if the absolute value of x minus c is less than delta, that means that, there's also a negative delta that exists in which c is greater than negative delta. So that just means that there is a domain of values such that negative delta and delta encompass the x value c. And if that exists, that also implies the existence of an f of x, which, if f of x is equal to L, or not, yeah, so I'm going to use L. I don't know why I switched up there, but we have, this is like the y-axis right here. If this is x, this is y. So with this y-axis, we'd say that for, since it's also the absolute value, there has to be a negative epsilon that is lesser than L. And since this relationship exists, where there is a domain of negative delta to delta, in which c is in between, there is also an existence of a relationship between L and epsilon, where L is encompassed between positive and negative epsilon, and as this value, the absolute value of x minus c, gets, well, not, sorry, as delta gets smaller. So as delta approaches 0 or gets smaller, then epsilon gets smaller as well and approaches 0, which means that as this becomes more and more narrow, this also becomes more and more narrow. And this expression means that x is getting closer to c. So if delta is approaching 0, x is approaching c, because we are getting more and more precise. And as epsilon approaches 0, L is approaching, or not L, but y is approaching L, which means that the y value is getting closer to L, since this is becoming more and more narrow, and this is becoming more and more narrow. F of c is approaching to L. And I know this is kind of cluttered, but I've already talked about this a little bit. But, yeah, the reason why the reason why it's not continuous at x equals c, if we're going back to our f of x is equal to the square root of x, the reason why it's not continuous at x equals 0 is because our formal definition of a limit has the absolute value of x minus c is less than delta, or the absolute value of x minus c is less than delta and greater than 0. We are not, I'm not going to underline that because then it would look wrong, but we're not using less than or equal to. We're only using the less than sign, which means that x minus c is not equal to delta, and x minus c is not equal to 0. For any value of x, for any value of c, you're not going to get any place where x minus c is exactly equal to delta, and x minus c is exactly equal to 0. That means that even if x minus c gets impossibly close to 0, or x gets impossibly close to c, x will never equal c. And as this domain of delta gets smaller from both sides, remember, because c is in between negative and positive delta, we're going to say that because of all of this, x will never equal c, and there has to be values on both sides. There has to be values on both sides for a limit to exist. If f of c is equal to L, and L is equal to the limit as x approaches c of f of x, from both sides, there needs to be values. There needs to be values on the left, and there needs to be values on the right, because x will not equal c. And if x can never equal to c, and there are values both before and after, since we have this idea that negative delta is less than c, which is less than delta, which means that c is kind of like in between the positive and negative deltas. We're saying that there has to be values on both sides of c for a limit to exist at c. And that will get us into when a limit exists. But just to answer our question, endpoint discontinuity, that means that for f of x is equal to square root of x, and we have this function right there, f of x is not continuous at x equals 0. It's not, because, I don't know why I put not equal to 0. the x is equal to 0, but it's discontinuous because there is no value. Let's go back to our delta notation. There's no negative delta right here, and there's no positive delta here. There is a positive delta, sorry. So for these negative deltas and these positive deltas, maybe the positive delta can get really, really close to C, even though it'll never equal delta, since you have that x minus C is less than delta. It's not going to equal delta, but it could get really close to delta. And while that might exist, there is no values in that area, that region right there. There's nothing there. So if there's nothing there, there's no negative deltas that can get closer and closer to 0. So there's no limit at x equals 0. And if there's no limit, then it's not continuous. And a long, arduous explanation, but yes, at the endpoint of these functions, can't really come up with anything else just off the top of my head, but even for like a random function like, x squared, but I'm not going to complete the x squared. Even for x squared, and then you just stop at like x equals 1 or something. On the interval of like -8 to positive 1, on this interval, let me actually define f of x. If f of x is equal to x squared, such that for every x that is less than or equal to 1, there is some type of value. There's no positive delta in this case surrounding our 1. So there's no limit at x equals 1 from the right side. So the entire interval from -x to 1, for not -8, but from, it is -8, sorry, from -8 to 1, not brackets, but closed brackets, from -8 to 1, f of x is not continuous, because at the value x equals 1, there is an f of 1, but there's not a limit as x approaches 1, because there needs to be values from both sides. And now, after talking about all that continuity and discontinuity nonsense for an inappropriately long amount of time, let's finally get to when does a limit exist. And I promise, this one's easy. A limit can only exist when it only exists when the limit as x approaches c from the left, which I'll denote as c minus. It's not c to the minus, it's kind of like a notation to say that on the interval from -infinity to c, there has to be some type of, there's stuff happening, basically. In between -infinity to c, there is stuff going on. And we're saying that as x approaches c from the left of f of x, it must also equal the limit as x approaches c from the right, which I will use a plus for. So you might even think of negative and positive as like negative and positive infinities. So a limit has to only exist if this is true. And if we think about our discontinuities, we have removable, jump, infinite, and endpoint. And you might be thinking that one of these is not like the other in terms of whether there is a limit or not. And that is removable. Removable discontinuities still do have limits. If we go back to our x squared, and we look from both the left, I know I put the right first, but if we look from both our left and from our right, there are values that are tending towards some f of c. So even though f of c does not exist, there are values from both the left and from the right that are approaching x equals c, and values from the top and from the bottom that are approaching L, if, the limit as x approaches c of f of x is equal to L. So removable discontinuities do still have limits. And you might even think about changing our definition of continuity such that if the limit as x approaches c from the left and from the right, if they both equal each other, another condition where c has to be exist is this. And that just comes back to our original part of continuity. If f of c is a value and the limit as x approaches c from both the left and from the right approach that c value, then this function is continuous. Okay, I know I went on random tangents. I think I talked a little bit about cardinality when it's completely irrelevant. But I hope now you can see when a function is continuous and when a function is not continuous. And while that's important, I definitely should have done that way earlier. Yeah, no. Like, that was pretty negligent of me. But now, we're just gonna fast track it into more advanced limits, and we're gonna talk about indeterminate forms. Let me write that down. Indeterminate forms. And well, this is gonna take a while. Already, I've gone way further in time than I thought I was gonna be just to get to indeterminate forms. So I think this might take another hour or so. But I mean, let's just start with thinking about L'Hopital's rule. If the limit as x approaches infinity of f of x evaluates to 0 over 0, or not evaluates, but tends towards 0 over 0, or infinity over infinity, then the limit, not f of x, sorry, f of x over g of x, if the limit as x approaches infinity of f of x over g of x is tending towards 0 over 0 or infinity over infinity, then we can say that the limit as x approaches infinity of f of x over g of x is equal to f prime x over g prime x. And yeah, that's just, I proved that previously, so I don't want to talk about it too much, but I'm just showing this as a way to show our first two indeterminate forms, and probably our most important ones, 0 over 0 and infinity over infinity. I might have talked about it beforehand, but 0 over 0 cannot evaluate to any real number. You might even say that, like, 0 over 0, you know what, I'll write this in a different notation, just to maybe make you think of something. So, if a set is just an assembly of elements, then the set, let's say the set A, capital, of elements are in real numbers. I know this is kind of crazy sounding, but I might have mentioned it before. That symbol just means in, so this whole statement means real numbers, plural, are, so the set of elements in which r is a real number, such that r is equal to 0 over 0, this is empty. I know this seems crazy, but if we just think about it, we're saying that for every real number r, if r was to evaluate to 0 over 0, that is not a real number. And that's not a proof. That's not really anything. I just thought it might be maybe a good example for you to see some notation in action. But yeah, 0 over 0 is not a real number. Even though 0 and 0 are both integers, and technically, no, you can't. No, sorry. Ratios have to be natural numbers. It has to be natural numbers so that you can get a a ratio that is a real number. So yeah, 0 over 0 is not a real number. Infinity over infinity is not a real number either, because infinity is not a number. But with these, we have our first two indeterminate forms, and we're going to call these type A. I don't think I need to explain why they're indeterminate. I guess let's define indeterminate first. Indeterminate means that you can't determine a limit in the way that your form is currently in. So for 0 over 0 and infinity over infinity, we had to do something to get anywhere with that, and we had to use L'Hopital's rule. So I'm going to put that with our first two indeterminate forms, not 0 over 0 is equal to infinity over infinity, but we have these two indeterminate forms, so we're going to call these type A. These are the nicest indeterminate forms that we have. And I like to, this is kind of a dumb way to think of it, but I think I might have said it in a previous video. Indeterminate forms that are not type A, the only way to evaluate indeterminate forms to get to an actual value that exists is you have to make an impossible result slightly less impossible, and then do the impossible to make it possible. I know that's not like math or anything, but I just think it's kind of funny that you have to make already impossible forms, which I will get to in just a second, less impossible so that they become type A. And you have to make these impossible forms into possible forms that exist, like, an actual ratio. I always thought that was interesting. But these are our two type A indeterminate forms, and every other indeterminate form will eventually get to type A with a bit of manipulation. And so with that, I'm actually going to try and give you guys some potential determinate and indeterminate forms, and you're going to have to see if there's something to do with these. So if we've already covered 0 over 0, that was a weird 0. If we've already covered 0 over 0, I don't know why I keep putting equals, then what would 0 over infinity be? And in that same vein, what's infinity over 0? And, you can keep on going. How about, let's say, 0 times infinity? And let's say infinity plus infinity and infinity minus infinity. And let's say 0 to the power of 0, 0 to the power of infinity, infinity to the power of 0, 1 to the power of infinity, 1 to the power of 0, and I was thinking about putting 0 to the power of 1, but you already know that. So let's look at all the things that we have. Well, I'm going to erase 0 over 0 because we already talked about that. And I'll put 1 over 0 up there, but I'm just going to work across, and we'll get to the 1 to the 0 at the very end, but I think you already know what that one would be. So 0 over infinity, there's no trick here. 0 over infinity is equal to 0. Well, actually not equal. It's trending towards 0. Since we're only working with limits, not the actual, like, value itself, so I'm just going to say it's tending towards 0. And, I mean, it makes sense. 0 is a small number. Or, well, when you're doing any limits, it's going to be a small number, like, I don't know, 0.000001, because it's not actually going to be explicitly 0, and that might give you a hint on how to find some of these other forms or how to think of them. And then infinity is obviously a very large number. So a small number divided by a very large number, like very, very large numbers, is obviously going to be a small number. So 0 over infinity is determinate. I'll just circle the ones that aren't determinate. And let's talk about infinity over 0. This one is slightly more difficult to think of. If we can go with our large number, small number thing. Oops. Small number. Okay. So with that, whoops. So with that, I would actually want you to think about this again in terms of that negative delta and delta. Since there is a negative delta, and since our c value in this case is 0, and there's a positive delta, that means that you can either have a very, very tiny negative number, like I'll put a dot 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 1, or you can have a very tiny positive number, not negative, 0.000 dot 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 1. And since it's not actually equal to 0, this form, surprisingly, is not indeterminate. This is a determinate form with a very large number. Let's even think about this as like 1 million, which is obviously very, very small in comparison to infinity, but we can think of infinity as a million for now. And if 0 is, it's not actually 0, we're getting close to 0, so infinity over negative 0.000001 is going to be a very, very small number. It'll be like negative 1 billion or something. I don't know off the top of my head, but it would be a very small number. I guess not really small. I kind of have trouble thinking of it that way too, because 1 billion's obviously a big number if it was a natural number, but negative 1 billion is very it's very negative. So if 0 was approached from the positive side, if we were having 0.00001 and infinity was still a million, then a million over 0.0001 is going to be much bigger. So yes, infinity over 0 will have a determinant form, because you can calculate this. Even though you can't divide by 0 in real math, since we're doing limits, you're not actually using 0, you're using numbers very close to 0. And now, let's talk about 0 times infinity. 0 times infinity is an interesting one. Using the rules of 0. 0 times any number, like n, is equal to 0. But 0 times infinity is kind of weird to think about. So, with this 0 times infinity, there's quite a few reasons why this is indeterminate. But one of the more interesting ways, in my opinion, is 0.000 dot 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 1. I'm just gonna, I know I've said this like a little bit, but 0.00001 is what 0 is technically equal to. I'm not even gonna think about the negative right now, but 0.0001 is it's not exactly 0, so it has to be just a very tiny number that is approaching 0. Like as x is approaching 0, x is not actually 0, x is just getting close to 0. So with this 0.00 bunch of zeros, 1, and infinity is still, actually I'm not even going to use infinity. I'm going to use, or not that I mean not use infinity. I'm going to not think about this in terms of million, but I'm going to actually try and think of this in terms of infinity. Like, if infinity is just some crazy number, again, infinity is not a number, but as an idea, we can kind of come up with some like concept of infinity that we can calculate with. If infinity was this crazy astronomically large number, then even times a really, really small number, you're going to still have a value. 0 times infinity will still equal something. But that doesn't align with our rule that 0 times n equals 0. So if 0 times infinity equals something, perhaps that something could also be infinity. Perhaps even if this 0 is really, really small, infinity is just so incredibly large that 0 times infinity is equal to infinity. And on and on. You can just contradict yourself as much as you want, but at the end of the day, 0 times infinity is not a valid expression. So this is an indeterminate form. And now infinity plus infinity. I think you might have already guessed this by now, but this one, kind of not following my own rules. I'm going to circle the ones that are determinate forms and leave the uncircled ones. Actually, no, that's dumb. I'll just erase this and circle the ones that are indeterminate forms. And neither this nor this are indeterminate. So I don't know why I circled that in the first place. But anyways, 0 times infinity is indeterminate. Because, it could be anything. And, you can just constantly contradict yourself. And if there is any contradiction in your internal logic, then that's not a determinate form. You can't do any math with it if it doesn't follow the rules of math. And now infinity plus infinity, you might have guessed this already, but a big number plus a big number is going to be a big number. Yeah, it's kind of obvious, I think. Infinity plus infinity is just infinity. And then infinity minus infinity is actually something that is a little bit weird, in my opinion. It's kind of hard to think of, but, if we go by our logic of any number minus the same number is equal to 0, infinity minus infinity should equal 0. But, like I tried to illustrate, infinity is not a number. The cardinality of n, which is the set of natural numbers, the cardinality of z, which is which is all the integers, and the cardinality of q, which is all the rational numbers, are all equal to one another, and they're all countably infinite. Even though, our logic might tell us that, q is more elements than z, because there's a bunch of, ratios in between every integer. So with infinity minus infinity, infinities are different, and this infinity might be larger than this infinity, or this infinity might be smaller than this infinity. That's the that's the same thing. This infinity might be larger than that infinity. But yeah, infinity minus infinity, you can't come up with a numerical value for this expression. So this is going to be another indeterminate form. And now 0 to the power of 0. This one is, I feel like there's a lot of debate about what 0 to the power of 0 even is. So that obviously just implies that it is an indeterminate form, because 0 to the power of 0, it could be 1 because anything to the power of 0 is 1. It could be 0 because any exponent with base, I put 1 there. Any exponent with base 0 is equal to 0. Like 0 squared is 0, 0 cubed is 0. It could even be, if we go back to our point 0, 0, 0, dot, 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 1 to the power of 0.000, dot, 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 1, even though it's a very small value, obviously, it's gonna be a value, and that value is not exactly 0. So with that, it's kind of hard to say if you would even get a result from this. So that means that 0 to the power of 0 is indeterminate. And now, well, we're going to get into some of the more interesting ones, in my opinion. So with this 0 to the power of infinity, I think this one, and this one's not super interesting, but, if we go back to our rule of 0 to the power of any number, or any exponent with base 0 is equal to 0, infinity, if we're trying to treat it as a number, we have to be equal about it. And if infinity is supposed to be treated as a number, then 0 to the power of infinity is going to be 0. So this is a determinant form. And you might even think of this as an actual limit. If you have f to the x is equal to 0 to the x, and you're trying to find the limit as x approaches infinity of f of x, then every single value is going to be 0 except for x equals 0, because of the indeterminate form that we were talking about. And so 0 to the power of infinity is equal to 0. And now infinity to the power of 0 is an interesting one. Again, I know if we try to treat infinity as a number, then you'd have anything to the power of 0 is equal to 1. But 0 is just being trended towards, it's not actually 0. So infinity to the power of 0.000 dot 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 1, it's still gonna be infinity. That's because, again, infinity is so incomprehensibly large that even if you do it to such a small power, it's still gonna be infinity. And yeah, even if it's to the trillionth root of infinity, you're still gonna have infinity. It's still gonna be a number. And that doesn't fit in with our idea that anything to the power of 0 is equal to 1. So with that contradiction, then we have to know that infinity to the power of 0 is not an actual thing that we can calculate. Next, we have 1 to the power of infinity. Wait, am I missing something? Hold on 1 second. Okay, no, I'm good. Never mind. So with this next one, we have 1 to the power of infinity. And now our brain is just yelling at us. Oh, it has to be 1. 1 to the power of n is always going to be 1. But again, we're not working exactly with 1. We're working with either 0.999, repeating, or we're working with 1.000 dot 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 1. That's what we're working with. We're not actually working with a real 1. We're working with a general trend towards 1. So with that general trend towards 1, if we have um, 0.9 repeating to the power of infinity. Well, let's think about that. Um, it's gonna be a value, and it might be very small, but it's still a value. Uh, so, and since this value is gonna be very small, so just like think about it like it is a fraction. Let's even simplify it just to 9 over 10. It is a fraction. So 9 over 10 to the power of infinity. Well, let's not even use infinity. Let's use 10. Sure. This is a super simplified version of infinity to the power of 0 if infinity not infinity. This is a super simple version of 1 to the power of infinity if 1 was approached from the left and infinity is just a really small number. 9 over 10 is going to be larger than um, I mean, let's even simplify it further. Let's say instead of 1 to the power of infinity, which is kind of a mean thing to give, let's use 9 over 10 to the power of 2. That one is super easy. We know it's going to be 81 over 100. 9 times 9 is 81, and 10 times 10 is 100. And 9 over 10 is equal to 90 over 100. 9 over 10 times 9 over 10, and on, it's going to be smaller than 9 over 10, which means that like 0.99999 to the power of infinity, that's going to be equal to 0. So 1, if approached from the 0.999 route, is equal to 0. 1 to the power of infinity. And now let's think about it in the other way. 1.000 ... 1. This might be a little bit easier to think about, but this is a number that is greater than 1, obviously. And anything times itself that is not 1 is going to be greater than itself. For every value of x squared other than like 1 or 0, x squared is going to be greater than x. That's how it is. So, 1 to the power of infinity, since 1.00001 ... 1 to the power of some enormous number, like on and on, that's gonna be infinity. It might take you a very long time to multiply a bunch of these numbers that are super close to 1, but to get a value that's actually like significantly larger, but it's gonna be infinity. So there's obviously a contradiction there. And we have 1 to the power of infinity. And now I saved the easiest one for last. 1 to the power of 0 is just going to be 1. So that's actually just an expression that you can evaluate. So let's talk about our 5 indeterminate forms that we've come up with. With these 5 indeterminate forms, we have we have 0 times infinity, infinity minus infinity, and we also have not 0 to the power of 0, 1 to the power of 0, 1 to the power of infinity, and infinity to the power of 0. These are all indeterminate forms, and they also fit the type system. We have type B and then type C. And this might seem kind of arbitrary, but there's actually a pretty good reason why we're splitting B and C. That's because B and C, well, let's say that B is just easier to work with. 0 times infinity, like if I had a function, not a function, but if we had a limit x approaching infinity of f over x times g over x, this is definitely going to be easier to work out than maybe a limit as x approaches infinity of f of x to the power of gx, which can result in quite a few weird things happening. And I mean, that's not like a proof or anything, that's just kind of common sense. This is going to be easier to work out than any of the power stuff. So let's think about this. How would we make any of this workable? There has to be something that we can do to make these functions even possible in the first place. So again, in order to work with these, we need to make them less impossible. We have a bunch of impossible situations that we are attempting to make less impossible so that we can make it possible. And with our first indeterminate forms, 0 over 0 and infinity over infinity, the least impossible of the impossible things that we've looked at, we know that we can use L'Hopital's rule for these types of functions. We can do the derivative of the top function and the derivative of the smaller function. So in order to work with 0 times infinity, let me erase these type C indeterminate forms for now. In order to work with 0 times infinity and infinity minus infinity, well, we're going to have to try and transform this into some type of quotient or some type of thing that might get us to something possible. So I'm gonna actually have two cases. If we have 0 times infinity and we try to make it into something that is L'Hopital-esque, it would have to be either infinity over infinity or 0 over 0. And that kind of gives me a couple ideas, because we know that 1 over infinity is a fully determinate form. It would be 0. And we know that 1 over infinity, if infinity was to act like a number, let's not use infinity because we don't know, since infinity is not a number, but if we had 1 over n, that's just 1 times n over 1 if we flip that fraction at the bottom, so we're left with n. So if 1 over infinity tends towards 1, and 1 over n should be n for any, like, anything that we're doing, we can actually kind of manipulate some stuff a little bit. This is going to sound crazy, but with 0 times infinity, if we regard infinity as n, let's say that n is equal to infinity, and we're going to treat infinity as the number n that we're using. If 0 times n is what we're given, we can also do, actually, let me change 0. Let's make that, I'm not even going to use n. I don't know why. I'm going to do f of x and g of x, because I think that might be a little bit easier for actual application. You might want to write this down. The limit as x approaches c of f of x times g of x is obviously some type of case that could eventually become 0 times infinity. Maybe this would become 0 and this would become infinity, or vice versa, but since it is a product of two functions, well, since 0 times infinity is a product of two numbers, which we're going to try and treat it as, you're also going to have a product of two functions. And we're going to try and make this the limit as x approaches infinity. Let me write the case that I'm going to work with. Oh, whoops. Okay, actually, I'm getting a little bit ahead of myself. So, we're going to let c be some value. We're not going to worry about x approaching infinity right now, because, I mean, while that's probably where this is going to go, let's try and make this as broad as possible. So let's say that the limit as x approaches c of f of x is equal to 0. And let's say that the limit as x approaches c of infinity, not of infinity, is infinity. Not for f of x, but for g of x. Sorry. Um, the limit as x approaches c of g of x is equal to infinity. And the reason I'm using c is because it could be positive infinity, it could be negative infinity, it could actually even be a value for one of these, but it's hard to just like say unless you're actually given the problem. So with these 0 and infinities, let's say that this is L1 and this is L2. We can write this as, actually no, I'm not going to do that notation. I feel like it might get a little bit too weird. But remember, 0 times n is also equal to 0 times 1 over 1 over n, if we're trying to make this act like a number. So with 0 times infinity, if we're trying to get to something that resembles, say, 0 over 0, and we know that 1 over infinity tends towards 0, and infinity can become 1 over infinity by putting a 1 over it, the limit as x approaches c of f of x times g of x is equal to the limit as x approaches c of 1, not 1, of f of x over 1 over g of x. And I think that makes sense, you know? We're just trying to rewrite this in a way that we can get, eventually, this infinity into a more workable form. And this obviously goes towards 0, or both of these will eventually tend towards 0. Because, again, you know, just using this thing, the limit as x approaches c of f of x is equal to 0, and 1 over g of x, if, well, not 1 over g of x, but the limit as x approaches c of g of x, if that's equal to infinity, then 1 over that, or 1 over g of x, the limit as x approaches c of that, it's going to be 1 over infinity. So we have a 0 over a 1 over infinity, which again is 0. So we're left with 0 over 0. So maybe write down this much, minus the equal. But yeah, that's how you would try to get to 0 over 0. And now let's look at it the other way. Let's try and get to infinity over infinity. So with infinity over infinity, it's going to be kind of similar, but I'm actually going to talk about another case. I know we did all our 0 to the zeros, and we tried to do a bunch of stuff, but I think I might have forgotten to use 1 over 0, which I think is a pretty interesting one. Again, logic would tell us that you can't divide by 0, which is true. But again, let's think. 1 is going to be 1. It's a constant. It's not like a limit that is approaching 1. But 0 is not actually 0. It's a 0.00 dot 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 1, or it's negative that. So 0.000 dot 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 1, or it could be negative 0.000 dot 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 1. So this can either be plus or minus infinity. Again, how does that work? Well, 1 is a constant. It's a number that's going to stay there. But any number over a really, really tiny number is going to be a big number. I mean, you can think about this in terms of fraction division. You can maybe express the bottom number as like 1 over a billion, you know, dot dot dot. And we already shown that 1 over n is equal to n. So 1 over, so n in this case would be infinity. So 1 over 0 could either tend towards infinity if we're using a positive 0.00001 or negative 0.001, which would obviously result in a negative infinity. So 1 over 0 can tend towards infinity, which is great. It truly is great. We can actually do something with that now. But Yeah, so with this, we can actually kind of work with this, and we can make this into an infinity over infinity. Let me erase these so I can circle them again. We have 0 and we have infinity, but again, 1 over 0 can tend towards infinity or negative infinity, and infinity is obviously going to be easier to work with, even if it was negative infinity, because we can just bring the negative out there. But yeah, so with this, the limit as x approaches c would be, if we're trying to get to infinity over infinity, well, we have our g of x, which is going to be g of x at the top, and then we have 1 over 0, which again, it's going to be infinity because 0 isn't actually 0, it's just a really small number, and 1 over any really small number is going to be a very big number. So we're going to be 1 over f of x. And so this is going to tend towards infinity because we said so, and this is going to tend towards infinity because 1 over 0 tends towards infinity. And yeah, maybe write that down a little bit. Essentially, if you want to get from 0 times infinity to 0 over 0, it's going to be f of x over 1 over g of x. And if you're trying to get to infinity over infinity, it's going to be g of x over 1 over f of x. And so with that, let's erase this. And now let's talk about another interesting case. Let's talk about infinity minus infinity. So this one, it's going to be a little bit easier to write, I guess. We're going to have the limit as x approaches c of f of x is equal to the limit as x approaches c of g of x. And I'm not saying that f of x is equal to g of x, because f of x could be, x squared, and then not f of x squared, but f of x. I don't know. I don't want to confuse you, but I think you guys can understand that f of x can equal x squared, and g of x can equal, x cubed. And even though both tend towards infinity, they're obviously not the same function. I'm just using this limit equals for the sake of brevity, but I guess I'm already talking too much about this. So let's write this in a slightly different way. We know that 1 over infinity equals 0. So actually I'm going to get the, let's see, I think I'll do the more difficult one right now. Let's try and get this equal to 0 over 0. And let me say we have the limit as x approaches c of f of x minus g of x. That's what we're given. And so in order to get this into a form of a quotient, this seems like it's going to be kind of weird. And it is a little bit weird. So we, as our foremost rule, we know that 1 over infinity is equal to 0. And if we're trying to find the limit of 1 of f of x, and that's also going to be the same limit as 1 over g of x, which is 0. So keep that in our back pocket. We know that the limit as x approaches c of 1 of, as x approaches c of 1 of f of x is going to be 0, and the limit as x approaches of c of g of x is also going to be 0. And so let's try and make something of this. And actually, you know what? Let's think about this again a little bit. Infinity times infinity. I'm not sure if I did that one, but infinity times infinity. It's not as weird as infinity over infinity or infinity minus infinity. It's pretty simple. A big number times a big number is going to be a big number. And there's no tricks around that. Infinity times infinity is infinity. So 1 over f of x times g of x, if we're trying to express 1 over infinity in terms of f of x and g of x, not just one or the other, then we would be able to write this in a different way. And let's think about this also in terms of, let's say, yeah, fraction subtraction. I know that sounds kind of dumb, but we have a number 1 over n, and we have a number 1 over n1. Sure. The only way to do this would be to have n1 times n minus, n. I should not be using this many n's. Let's make this n1 into like a x. No, we're already using x. Let's make it into an a. Sure. This is going to be an minus na. Wait, what? Oh, sorry. Never mind. With this 1 over n, it's going to be a over an, and this 1 over a is going to be n over an as well. So you're going to be left with a minus n over an. And if we have this 1 over f of x times g of x, and we have our 1 over f of x and 1 over g of x, and they all tend towards 0, we can write this as the limit as x approaches c. Stay with me here because this one's going to be kind of weird. Of 1 over g of x minus 1 over f of x all over 1 over f of x times g of x. I know this seems like a lot, and it is a lot, but it does kind of follow our a minus n idea. You have the number 1 over g of x and the number 1 over f of x. Let's even write this in terms of a and n. We can say that if 1 over f of x equals n and 1 over g of x equals a, then we could do some manipulation. If f of x minus g of x is equivalent to infinity minus infinity, we can make these into fractions such that a minus n over an is equal to 1 over n minus a. And that's exactly what we've been trying to do, right? If 1 over f of x is 1 over n, then n is equal to f of x. And if we're trying to do 1 over n minus 1 over a, we can make these in terms of 1 over g of x and 1 over f of x. So I know that was a bunch, and it might be a little bit conceptual, but I hope you kind of get how we got to this 0 over 0. Because we're just trying to make infinity minus infinity in terms of fractions, because we know that 1 over infinity tends towards 0. So with that, let's get into the second case, that being, actually you might want to write this down. This is definitely going to be useful for you for like trying to solve these type B indeterminate forms. And our last case, or not our last case, but our second case is infinity over infinity. And this one, I think, is pretty sensible. Like, so, I didn't say this, but we know that e to the power of infinity is infinity. Since e is not equal to 1, it's not equal to 0, it's an actual number that is greater than 1 and greater than 0, we know that e to the power of infinity is going to be infinity. And we know that ln of e, or log base e of e, is going to be 1. So ln e is going to be 1. And that's kind of an interesting thing. Even though we have infinity minus infinity, we're still working with infinity. We want this to be a quotient. And the only way that sticks out to me is making this a quotient in terms of ln. Now, I don't think I have the time to show proof for natural logarithmic properties and natural logarithmic properties, but I am certain that at some point you might have seen ln minus a. Oh, ln of a minus ln of b is going to be ln of a over b. And that's really useful if we have infinity minus infinity and we're trying to make that into a quotient. So if we know that ln of e is equal to 1, ln of e squared is equal to 2, so ln of e to the power of n is going to be n. That's because, logarithms, if you have base e of e, then any number here is going to be, this e to the power of that. So we know that ln of e to the power of something is going to be that something. So this kind of comes together in a nice way. We know that the limit as x approaches c of this is going to be ln of e to the power of f of x. So let's, instead of using n, let's actually write it out. We'll say that if this limit as x approaches c of f of x is some number, we can do e to the power of f of x. I almost put like that little caret thing, but ln e to the power of f of x is going to be f of x. And if f of x tends towards infinity, we know how we can get to infinity over infinity. We would have the limit as x approaches c of the natural logarithm of e to the power of f of x over e to the power of g of x. And I know all this seems kind of complicated. I will try to do some type of worked example thing in a later video, but yeah, this is how we would convert this into an infinity over infinity situation, because we know that e to the power of infinity is infinity. We know that we can do this operation, we can make it e to the power of f of x, and we know we can make it to the power e to the power of g of x, and we know that these are both going to go to infinity, and we know that ln of this, if we're going to write this as f of x minus g of x, we can also write this as ln of e f of x minus ln of e to the power of g of x, because ln e is just a operation that will eventually evaluate to 1, and any subtraction of natural logarithms is going to be a quotient. It's going to be that first thing divided by the second thing. So all of that, you'll have ln e f x e g x, and that's pretty cool to me. We can express this kind of simple. Just, we know that it's not easily calculable, but in our heads we know it's a little bit simple. We can make it slightly more complicated, but just more workable. And so with this, we can actually try and make this even simpler. You can switch the order of ln and the limit, because ln is a continuous function, and we'd say that the ln of the limit as x approaches c of e to the power of f of x and e to the power of g of x, that's going to be infinity over infinity, which is exactly what we want. So yeah, maybe write down this part, but we're going to go straight past our type B indeterminate forms into type C indeterminate forms. And now we're going to get into some, I wouldn't say too crazy, but it can get a little bit conceptual. So we have our limit. We have our, not our limits, but we have our indeterminate forms of 0 to the power of 0, 1 to the power of infinity, and infinity to the power of 0. These are our type C indeterminate forms. And so let's start with our first one. We have the limit as x approaches C, f of x is equal to 0 plus. This might seem weird, but again, if we have a function such like x to the power of x, 0 is our endpoint, and there's not going to be anything. X to the power of x is a bad example, sorry, but we're not going to have anything approaching from the left. It's going to be approaching from the right. So there has to be a hard limit coming in from the right. It's not coming in from the left. So it's going to be 0 plus, even though we're still going to treat it as, 0. So with that, we have the limit as x approaches C of g of x is equal to 0, just regular 0. I know I feel like I'm contradicting myself a little bit, but we're saying that if f of x to the power of g of x is a legal operation, you can't use a negative tiny number there, because then you'd have like an oscillating thing, and it might get hard to work with. So with that, how would we make, let's actually start with 0 over 0. How do we make the limit as x approaches C of f of x to the power of g of x? How would we make this become that? And this is where we're going to get into some complicated stuff. Well, given f of x to the power of g of x, we're going to have to do something I think that's pretty interesting. We're going to use our, if we think that ln of e, let me even put e to the n, is equal to n, there's also an e to the ln of x equals x. And that, that makes sense. If we have 2 to the power of 1/2 times, actually no, bad example. It's just because they're inverse functions. It's like the inverse of e of x is ln of x, and f minus 1 of x is going to be just x. And you can even switch that. You'd have like the inverse of the actual function is also just going to be x. So with that, let's think, how could we make this into something that's more palatable? We're going to work with our 0 to the 0. So we're going to have 0 over 0. And using our e idea, well, actually, let me show a little bit more preparation. We have 0 to the power of 0, obviously, but we are trying to make this into a function that we've seen before. So I think perhaps the best way to do that would be to do, actually, let me, before I get ahead of myself, if we have f of x to the power of g of x, this whole statement is equivalent to e to the power of ln of f of x to the power of g of x. That's a lot of stuff, I know, but essentially these are two inverse operations of one another, and f of x and g of x, like f of x to the power of g of x, is what we've been working with. So I hope it's not too big of a jump to see why we're doing this. And now, using our ln properties, ln of x to the power of a is equal to a times ln x. And now, you might be able to see that we can bring this g of x outwards. We can take the exponent from f of x to the power of g of x, and we can multiply it by ln of f of x. So we are left with the limit, or actually I'm not even going to use limits. Let's just say that f of x to the power of g of x, I have no idea what's happening. One second. We're saying that f of x to the power of g of x is equivalent to e to the power of ln f of x times g of x. And I hope that's not too big of a leap. I hope you can see how we got there. But even if you do see how we got there, you might be wondering why any of that was necessary. With e to the ln x times g of x, you might already recognize this notation a little bit, and you might be able to see this is similar to our infinity times 0. It's a product of two things, so we might be able to do something with that. And that's true. We would be able to make a type C, well, not we would be. You always make a type C indeterminate form into a type B indeterminate form, and then eventually you'll be able to make it into a type A indeterminate form. But just so that we can have a little bit of mental exercise, let's try and make this type C into a type A. So we have 0 over 0, and we are given limits that approach 0 and 0. This is workable. I feel like we can do something with this. So I'm going to keep the limit. I'm going to use our nicer limit, the one that only approaches, not the only approaches, but the limit that approaches 0 from both positive and negative epsilons. So I'm going to use the nicer one on the top, and I'm not sure if I should do the E stuff right now, but like we can apply that E idea a little bit further. So if we apply our E to the ln of f of x times g of x into some type of limit, we can say that the limit of everything to the left of what I'm writing is equal to the limit as x approaches c of e of ln of f of x times g of x. And now, I don't know quite how to explain this. I guess you could say that since e to the power of x is known to be a continuous function, we can bring it outside, like how we would do any operations with ln. But I don't know of any proofs that could show that property of e to the power of x. But I'm probably going to do some type of video working through a couple of indeterminate forms, especially some really difficult ones, so that we can get from type C to type B to type A, and we can, run the gauntlet pretty easily. But I'm just going to show right now that e to the power of the limit as x approaches c of ln f of x times g of x is equivalent to the limit as x approaches c of e to the power of all that. And I can't really show you why that's equivalent. I guess it might be unsatisfactory, but e to the power of x is a continuous function, so we would be able to bring it out like how we would other continuous functions like ln of x. But yeah, this is equivalent to that. And so let's try and work with this to make some kind of value. We can have we have our ln of f of x, but we're trying to make this, instead of using, infinity times 0, which is a type b, it's something that we know how to work with now, but we want this to be type a. We want to immediately, we're trying to immediately get from type c to type a. And so with this, we know that 1 over 1 over n, did not draw a line there, 1 over n is equal to n. And with that idea in our head, we can kind of do something a little bit weird. So, let's see. Well, we know that this can be written, if this is f of x to the power of g of x, like, well, not that, but if all of this, if all of this is equal to all of this, ln of f of x is a number. And if we're trying to keep ln of f of x at the bottom, we could write this as the limit as x approaches c of g of x, not g over x, but g of x, over 1 over ln f of x. And I know that's a pretty crazy operation to even attempt to calculate, but it fits in with our current ideas. And since we're approaching from a positive value, there's no worries about, a negative input for x. Like, you can't do ln of a negative number because e to the power of whatever is not going to ever be less than 0. So, yeah, that's why we kept it as 0 plus. 0 is being approached from the positive side. So even though this limit is evaluating to 0, it's more like it's tending towards 0, specifically from positive infinity. And with that, you might want to write this down. Let me reaffirm that this is how we get to 0 over 0. We are just, if ln f of x times g of x is how we got from f of x to the power of g of x, then this needs to evaluate to infinity, so that we can get 1 over infinity, which would tend towards 0. So yeah, I might not have explained all of that the best, but this is how we would get from this limit to this limit. And I know this might be uglier to look at, but I wouldn't equation shame, but this is kind of harder to work with. So I feel like that's a valid criticism. But just as an exercise, we're trying to get from type C to type A. You might not do that, especially in your classes. You'd probably have to go from type C to type B. But I think this provides good practice for, trying to attempt harder limits in fewer steps and to find maybe shortcuts that are actually mathematically viable. And now let's talk about another case, that being infinity over infinity. So I actually erased too much. Let's get all that down. We're still going to have our limit as x approaches c of f of x to the power of g of x. But now, instead of trying to get to 1 over infinity, we're trying to get to, 1 over infinity. We're trying to get to infinity over infinity. And to get to infinity over infinity is, I wouldn't say it's more difficult, but it does require some good understanding of how limits work. Now, ln of f of x is always going to be, well, not always going to be greater than 0, but the x values will never be exactly 0. E to the power of x can never equal 0, regardless of what x is equal to. So that's why we're using 0 plus, so that there's no traps that we fall into in trying to find an ln that works for the situation. Now, in order to get infinity over infinity, well, let's think. We know that ln x tends towards positive infinity. That's kind of a rough sketch for the graph of ln x, and y equals 0 is a vertical asymptote, or sorry, x equals 0 is a vertical asymptote right there. But with x equals 0, ln x can never have an x value that is equal to or less than 0. And that's an important thing to think about. If c, which again, it's not a constant for our purposes, it's just a placeholder for maybe positive infinity, maybe negative infinity, we don't really know, but we're trying to keep it workable. It might even be some kind of a constant that results in an infinite value, even though I can't think of anything off the top of my head. But since we're trying to work with a c that's, again, not a number, it's going to be an infinity. The limit as x approaches c of ln f of x, in this case, is going to be infinity. Again, c is a positive infinity because we're approaching 0 from the right. That's what the 0 plus means. So this has to be infinity, like a positive infinity, ln of f of x. So if we know that ln f of x tends towards positive infinity, let me put an arrow so that you guys don't get any weird ideas about equality and tending, or I don't know. How do we get this g of x into something that's workable? And I'm pretty sure I talked about it, but 1 over 0, it's tending towards infinity. 1 over 0 tends towards infinity because 0 is not 0. 0 is a minuscule number, 0.000.1. And 1, we're going to keep 1 as 1. Even though it might not exactly be 1, it's going to be... Actually, no, it will be exactly 1 for the operation that we're trying to do, which is 1 over g of x. And 1 is a constant in that. So that makes this easier to think about. 1 over a really, really small number is 1 times a really, really big number. So 1 over 0 is going to be tending towards infinity. And now, if we know that ln of f of x is tending towards positive infinity, and 1 over g of x is also tending towards positive infinity, we know exactly what to do. We have our e to the limit as x approaches c, because this notation is going to be with us for the rest of our type C indeterminate forms. We need to use the e to the power function. Maybe like natural exponential function, I don't know the correct term for it, but we're going to use e to the power of something for all these indeterminate forms because we're trying to get exponents. We're not using basic operations like addition or subtraction or multiplication or division. We're trying to use exponents. So we're going to have to use exponents in our solution, and that exponent's going to be e because it works really nicely with ln. Now, if we know that ln of f of x tends towards infinity and 1 over g of x tends towards infinity, I don't know why I put 0, we're going to have the limit as x approaches c of ln f of x over 1 over g of x. And that is going to be how we would turn the indeterminate form 0 to the power of 0 into infinity. And yeah, maybe you might want to write that down. But I hope most of this is pretty, maybe not standard, but I hope you can at least see the steps of how we're getting to these ideas. And on that note, I hope that you also understand that we're not actually doing the L'Hopital's rule. So if we're going from type C to type A, and type A is 0 over 0 and infinity over infinity, we're not going to do the derivative of e to the blah blah blah, because that's just going to be the blah 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 prime times e to the blah blah blah, and that's not what we're trying to do. We're only going to do L'Hopital's rule in places that we can do it, and that is the limit. So if we're doing all of this like math, the limit as x approaches c of ln of some crazy function f of x and 1 over g of x, and a bunch of math is happening, eventually we're going to do L'Hopital's rule, but it's not going to be of everything. It's just going to be everything within those parentheses. It's going to be everything within the exponent. So yeah, that might catch you, but just know that you're not taking the derivative of the entire thing. You are just taking the derivative of e to everything in that exponent. And since you're only taking the, if you're only doing L'Hopital's rule to everything in the exponent, you still need to plug in your value. You might come up with a finite value like 0, and you'd get, not e, you'd get 1. Or you could get another finite value 1, you'd get e. Like, lots of things could happen, but you're going to have to plug that into e to the power of, like, x, if x is what you're getting. And so let's try 1 over, not 1 over, but 1 to the power of infinity. We'll say that limit as x approaches c of f of x is equal to 1. And then the limit as x approaches c as of g of x is equal to infinity. And again, this is going to be our routine f of x, g of x notation. So the limit as x approaches c of f of x to the power of g of x. And like always, we're going to try and find how we would get to 0 over 0. And again, this is going to be similar to our other thing. We know that, well, not similar to the other thing, but the same principles are going to apply. If ln of, let's say, a is equal to 1, then a has to equal, not 1, sorry, kind of spoiled it a little bit, but the ln of a, if that equals 0, a has to equal 1. And that goes for any logarithm with any base. If you have logarithm with base a of b, and that equals 1, b has to equal, I don't know why I keep putting 1 there. I mean to put 0. You were saying that a to the power of 0 equals b for that function. So b has to equal 1. I know I'm switching from a to b, but that's why any logarithm with any base a and any value b, that's going to be 1 if that evaluates to 0, because e to the power of 0 is equal to a, which means that a is equal to 1. So all of that is to say that if we were to try and make this 1 into a 0, we can think about this as ln of f of x. Because, again, ln of 1 is equal to 0. So, if ln of f of x tends towards 0, that will be, and we don't need to worry about anything too much. We know that 0 is easier to work with, or, well, 1 is easier to work with than than 0, which is being approached from positive values. So ln of f of x is tending towards 0. And we also know that from a bunch of doing stuff like this, 1 over infinity tends to 0. I hope by now that's fully ingratiated in your life. But 1 over g of x is going to be tending towards 0. And now we have this beautiful ln of f of x and this 1 over g of x. And now we know we can do two operations that will eventually tend towards 0 over 0. And now let's write it down. Using our e to the power of the limit as x approaches c of ln f of x times g of x, idea that we've been trying to use for our evaluation so far, we can instead write this as e to the power of the limit as x approaches c of ln f of x over 1 over g of x. And now we can do L'Hopital's rule on this because this is going to be tending towards 0 over 0. And after we do L'Hopital's rule on this, we plug it back into our function. We do our final output in the exponent of e to the something. And so, yeah, maybe write that down. I know I'm kind of skimming through this, but I will work through some of these examples. I'll try to work through an example of going straight from type C to type A, and then we'll do an example of perhaps a more cautious type C to type B to type A. And I hope you might even see where the type B comes from, because if we go back to e to the ln f of x times g of x, ln of f of x can either tend towards infinity or 0, and g of x can also tend towards either infinity, 0, or some constant. If you have a constant c that g of x is tending towards, or ln of f of x is tending towards, then the calculation is super easy. It's just normal stuff. But if if both ln of f of x tends towards infinity or 0, and g of x also tends towards infinity or 0, then you're going to have to do the type B tricks that we've been doing, and you'd have to make it into a quotient that you can do L'Hopital's rule to. So type C to type B might be, it's probably a little bit simpler, but I think it's a good exercise to think about this in a slightly different way. And now, let's go to our second case. Might want to, I'll erase this, it's been kind of scratched up a little bit. We have the limit as x approaches c of f of x equals 1, and then the limit as x approaches c of g of x equals infinity. And now we're trying to tend towards infinity over infinity. Again, I'll write out the limit as x approaches c of f of x to the power of g of x. And now let's think about this. So if we're trying to make this into an infinity over infinity type thing, well, we already have an infinity. That's already given to us. We know that g of x is tending towards infinity. And if we're trying to get to a 1 over, if we're trying to get to, I almost spoiled it, if we're trying to get from 1 to something that tends towards infinity, that's going to be a slightly harder operation. So, we already know, I think this is to the point of just being unnecessary. We know that 1 over 0 tends towards infinity if we're approaching this from a positive value. Even if we weren't, the negative value stuff doesn't actually do too much to us right now. If 1 over 0 tended towards negative infinity, we'd still be doing L'Hopital's rule, but we would factor out the negative. So, if we know that 1 over 0, just for the sake of, like, let's just say for the sake of ease, we'll say that 1 over 0 is tending towards positive infinity for now, and ln of 1 is equal to 0, and we already have 1, we can do what I think is a pretty fun operation. We can do 1 over ln of f of x, because 1 over ln of f of x, if f of x is equal to 1, that means that we are tending towards 1 over 0, which is tending towards infinity. And so, let's put it together. We have g of x, we have g of x, which already tends towards infinity, and we have 1 over 0, which tends towards infinity. And that 1 over 0 came from 1 over ln f of x. So with that, we can go to our final part. We will say that this limit is equivalent to e to the power of the limit as x approaches c of g of x, which is unadulterated in all its glory of being infinite, and then we'd have 1 over ln of f of x. And that's how we would make this part approach infinity over infinity. And that's how we would make this L'Hopital's rule-able. And so, yeah, maybe write that down. Just this part. And we will go into our final indeterminate form, that being infinity to the power of 0. And this is just going to be more of the same. In fact, it might even be a little bit easier to think about than that 1 to the power of infinity. I know that the f of x stuff might have gotten a little bit confusing. But we have the limit as x approaches c of f of x is tending towards infinity, and then the limit of g of x as x approaches c is tending towards 0. And now, this is just going to be more the same. If we have the limit as x approaches c of f of x to the power of g of x, in this case, we're trying to get to 0 over 0. G of x is, it's 0, you know, it's doing its thing, and we don't even have to bully it into becoming easier to work with. It's just going to be g of x is tending towards 0. And now, infinity, we could do some weird stuff, but we're trying to keep this relatively normal. But we know that we have to use ln in some way, shape, or form, because we're using ln of f of x times g of x in the exponent of e to the power of all that stuff. If we're trying to get to f of x to the power of g of x, ln of f of x needs to be there in some way, shape, or form. So we're going to have to do kind of an unnecessary operation, but we know that 1 over infinity tends towards 0, but we have to make this 1 over infinity come from 1 over ln of something. And that something is just very simply going to be f of x. And that's because since the graph of ln of x is tending upwards, and there's no horizontal asymptote, that means that ln of x is tending towards infinity. So ln of infinity, if we were to treat infinity as a really big number, ln of infinity is also going to be a really big number. So 1 over ln of f of x is tending towards 1 over infinity, which is tending towards 0. I know that felt like an unnecessary operation, but we have to use ln f of x if we're trying to make something that fits in with our f of x to the power of g of x. And now, let's put it all together. We're trying to get to 0 over 0. This is equal to e to the power of the limit as x approaches c of, so we know that g of x tends towards 0, and we know that 1 over ln of f of x tends towards 0 because that tends towards 1 over infinity, which tends towards 0. And now we have the limit as x approaches c of g of x over 1 over ln f of x. And now everything in those parentheses will be tending towards 0 over 0, and you'd be able to L'Hopital's rule. And now, last but certainly not least, we have our final case and our final indeterminate form, that being infinity over infinity. Again, you might want to write this down. Erased too much there. 0. I don't know why I erased that either. It's still going to be infinity and 0. But, you don't know. These sneaky zeros might become ones when I'm not looking. We have the limit as x approaches c of g of x equals 0, and then the limit as x approaches c of f of x is equal to infinity. And again, we're trying to get to infinity over infinity. Now it's f of x's turn to be nice and not do anything dumb. So f of x is going to be tending towards infinity. It's going to be in its unadulterated glory. But 1 over 0 is a problem that needs to be fixed. Well, actually, I missaid that. F of x is kind of sneaky about its awfulness. I'm kidding. We need to make this f of x into a ln of f of x. Remember, if we're trying to make this into ln f of x times g of x, which is the exponent of e. I know I've been kind of repeating myself quite a bit, but I really want to make sure that everybody knows how we are getting from type C to type A. We're skipping that step for getting to type C to type B to type A, which is probably the most normal way of teaching it, but I think this is more fun. So it has to be an ln f of x, but luckily it's not too mean, and we have ln of f of x is also tending towards infinity, because if f of x is tending towards infinity, ln of f of x is going to be tending towards infinity. I just repeated myself. I meant to say that ln of x is going towards infinity as x increases. And now, given 0, again, this isn't too hard. We know that 1 over 0 tends towards positive infinity if we're working with that. And we're just going to assume for now, because I mean, you could factor out negatives and do a bunch of stuff, but we're trying to make this pretty simple, or relatively simple. So 1 over g of x is going to be tending towards infinity in this case. And now we have the limit as x approaches c of f of x to the power of g of x for the last time is equal to e to the power of the limit as x approaches c of ln of f of x over 1 over g of x. And again, everything in the parentheses will tend towards infinity over infinity, and you'd be able to do L'Hopital's rule, and you might get something finite to plug into e to the, let's say, a. I don't want to use x because we've been using x all the time. And if a is the result of a bunch of L'Hopitaling all over the place, then you'd be able to plug in a into e to get your final limit. And now we know, I hope we know, how to get from type C indeterminate forms to type A indeterminate forms, but actually practicing that is a whole nother thing And unfortunately, it is a whole nother thing that we're gonna do later because I'm tired. So, yeah, I hope that was a fun video. Uh, Maybe not fun, but I really do like indeterminate forms. It always feels like a puzzle trying to get every single piece into place so that it fits with our established rules. And our album recommendation of the day, I I do really want to recommend "The House Is Burning" by Isaiah Rashad. And honestly, I do recommend it, but I feel like it only came out like yesterday, so I can't offer uh like I can't offer an objective opinion because I just haven't listened to it enough. But from my first impressions, it's just it's Isaiah's, you know, normal brand of cloudy, murky, but still rather optimistic production that has a little bit more trap inspired, maybe even neo soul in some of the latter cuts. But um, yeah, and wow, Isaiah seems to be noticeably less energy in comparison to some of his other um, albums. I do really quite like this in that this is not a like insult to the Sun's tirade because I do like that album as well, but his previous album was way too long. It honestly felt like it was 2 hours instead of like an hour and some change or however long it was. But this is a concise 49 minutes, and it's just a good album to maybe like, I don't know. I feel like this would be a good thing to listen to while you're driving at midnight on like the freeway. But I guess uh let me think. I don't have anything off the top of my head, but I think the the album that I've been kind of listening to quite a bit recently is it's Manger on McNichols. Uh, this is by Boldy James and Sterling Tolles, I think. And this album, this album is pretty insane. Manger by McNichols. I don't know if I'm pronouncing either of those correctly, but yeah, I I wouldn't even know how to begin describing this. Uh, I um so this is by Boldy James and Sterling Tolles. I don't know too much about Sterling Tolles' background. I know that this collaboration between the two was quite a long time in the like pipeline. I know that they've been working on this for just years now, and you can see it. Manger by McNoll's is like a weird intersection of like chamber jazz, like jazz with like a full all of the instruments. I can't. I'm trying to explain this in a you know way that's even barely lucid, but it's hard to describe this album. It's like jazz and like gangster rap, but it's not. It's not the normal jazz and gangster rap. It's like weird, because jazz rap has always been a thing. You have Del the Funky Homo Sapien. You have even some cuts by MF Doom, a Tribe Called Quest, De La Soul, The Far Side. You can go on and on. Jazz rap has always existed, and gangster rap has always existed. There's always been, you know, Freddie Gibbs's and Pusha T's, and you can even go further back to like I don't know, even NWA might count. But like, it's just, and like J Rock is a maybe a newer example, and some of the folks from Griselda might be considered gangster rap, but I I I don't know. This is obviously gangster rap, and this is obviously jazz, but while they do mesh well, Boldy James and Sterling Tolls are definitely in competition to see who can be the defining genre of this album. And in the best way possible, neither of them are winning. This is equally a gangster rap album and a chamber jazz album, and that's just it's just crazy to me. Like, I mean, it's not like it's abrasive or overly contradictory, but I wouldn't have imagined an album like this is possible. And other than that, I mean, just in terms of execution, I so out of the Griselda camp, I think that either Benny the Butcher or Conway the Machine are the best out of them. I think that Boley James, he definitely has like some interesting lyricism, though. I mean, all the Griselda folks talk about like just dealing drugs, and I mean like that's obviously a hustle, but it's just their content does overlap way too much, in my opinion, for just one collective. But Boldy James always has like a weirdly poetic, just despondent way of talking about dealing drugs, and the production obviously is interesting and varied, but Sterling Tolls does like fit that almost moody aesthetic by Boldy, and yeah, I think that's as much as I can say without like just kind of ranting. But Manager by McNichols is it's a stellar album. It's one of the most interesting rap albums that I've personally listened to, and I will definitely try to listen to more Sterling Tolls in the future because, yeah, it was weird. I didn't even do my outro. Dang. These days I've been slipping. But I hope you enjoyed this video. If you did, please comment down below. If you do not enjoy this video, then constructive criticism is always encouraged. And if you're not in the mood for constructive criticism or a comment, then let me come up with something. You can do, you can do a push-up plank. Okay. Bye.